Okay, so here we go. The last video, or maybe two videos, as far as lecture stuff goes, of the semester. Maybe two if this ends up running long. I'll split it up, but this is the last material I'm going to cover before the final. And I do apologize that it's coming out later than I wanted. Had some tech difficulties last night, but I think they're all fixed now. At any rate, what we're doing today is the last two more sections out of chapter 6. So the section 6.2 is more about functions. Just a little bit of another definition about functions and some ways that we can consider mathematical objects or mathematical processes you've seen before, how we can consider those as functions as well. And 6.3 is on some particular types of functions. Functions that are injective, surjective, or bijective. So injections, surjections, and bijections are what we're talking about. So first of all, and this is something that I kind of hinted at the last video, is when do we consider functions as being equal? Well, there's three conditions that have to be met. First of all, the functions have to have the same domain. Even if the functions look the same when you evaluate them at points, if they do not have the same domain, they can't be equal. They also have to have the same codomain. So if they don't have the same codomain, they can't be equal. And even, and the last thing is, for any x in the domain, they have to evaluate to the same point. So we saw an example in the last video where we had a function that was like, I think f was, this might not be exactly the same one, but it's the same idea. F was defined as a function from R to R where f of x was equal to, we'll just say 2x plus 4. And then I can compare that with another function, g, that goes from, say, z to z, and g of n is going to be 2 times n plus 4. Now, even though the way you would evaluate these functions is the same, you just take an element from the domain, multiply it by 2 and add 4. For g, you take an element out of the domain, multiply by 2 and add 4. Since these functions have different domains and different codomains, they can't be considered equal. So whenever you're trying to decide if functions are equal, check if the domains are the same and the codomains are the same, and they both evaluate on arbitrary points. Evaluate to the same thing on arbitrary points in the domain. Okay, so here is an example of something that's a function that you've been using for a while that you may not have realized is actually a function. We can consider the derivative of real valued functions, that is, taking the derivative of a real function as a function in and of itself. Now, if you've ever used Mathematica or Maple to take a derivative, you've already seen this in action. So one thing to think about would be, what is the domain and the codomain? So here's a little snippet from Mathematica to illustrate what I'm talking about. So this short video, I'm just going to show you on Mathematica how, if you've used Mathematica, you've already thought about the derivative as a function. How that works. So first of all, I'm going to define f of x to be sine of x squared. And so there's my function. Now, one way you can take the derivative on Mathematica is to just do f prime of x, and to give you 2 times cosine of x sine of x. But a way to make it a little bit more illustrative as a function is if I use the d operator. Now, this is how you would take partials, so I got to specify x, that's the derivative I'm taking. But think of this d as a function. Okay, it's a function that sends a function to another function. So this function takes as an input f of x, which was sine of x squared, sine of x, the whole thing squared. That's the input, and the output is another function, 2 times cosine of x times sine of x. Okay. Now, the reason we want to do this is we want to think about what would be the domain and the range of thinking of the derivative as a function. Okay, a function from functions to functions. Okay, so look at this example with absolute value. I don't know if you've ran across this issue with Mathematica or not, but to avoid any problems with, well, when I try to plot it or take its derivative, I want to specify I'm doing real absolute values. If you ever take complex analysis, this will matter to you. But I'm going to define g to be the real absolute value of x, which is just what we think of as the absolute value. So there's the function. Now I'm going to take its derivative, and it's x over real absolute value of x. So in other words, x over the absolute value of x. Okay. Now if we plot this, we're going to get what we would expect. Okay. Remember that the derivative of the absolute value does not exist at 0. Okay? It doesn't exist at 0. So when you try to plot this function as the derivative that it gives you, Mathematica doesn't really illustrate it, but this is a horizontal line when it's greater than 0 and a different horizontal line when it's less than 0. So think about what that means when we're trying to define the domain of the derivative operator. Okay. A little bit more extreme example would be like this one. K of x is going to be x over x plus 1. And then I'm going to go ahead and plot the function. So notice we have this infinite discontinuity right here. If I take the derivative, I get this. And if I try to plot the derivative, I still have that problem right there. Okay, I still have that problem right there. So in other words, what I'm getting at with the absolute value example and with this example is these are not differentiable functions. If we're thinking of differentiable meaning differentiable over all the real line, right? These have some places where they're not differentiable. And so these output functions are going to have these discontinuities. Okay, so think about what that means when we're trying to figure out what is the domain and the range of the derivative as a function. So what you just saw an example of is the following. I'm going to define a function d to be the derivative. So this function is going to go from a domain set, which for right now I'll just call it A, to a codomain set. And what the function does is if f is an element of A, then d applied to f is just going to give you the derivative of your function. So think about, what does A have to be in order for this to work? Well, I have to be able to get a derivative. So that means that A is going to be the set of real differentiable functions. Well, what does that mean? Let me make some more room here. That means that, for example, the function f of x equals x squared would be an element of A because that has a derivative. You know, all polynomials would have derivatives. The function f of x, let me not use f because I've already used it, but the function g of x equals the absolute value of x, this would not be an element of A because that function is not differentiable. And when I say differentiable, I mean differentiable on all the reals. So the absolute value of x is not an element of A because I can't take the derivative at 0. Okay. Now, that's the domain. The domain would be all differentiable functions, but what would the codomain be? Well, the codomain would just be the set of all real functions. And then the range, or the image of A, would be all functions that could be obtained by taking a derivative. Okay. Think about what that would mean in terms of like functions that you can take an integral of. Do you recall what we called functions that you can take an integral of without doing numerical stuff? Okay, those were called functions with elementary derivatives. So the domain of the derivative function is all real differentiable functions, and the codomain is the set of all real functions. And then, sit with and think about what that means the image of A or the range of A would be. Excuse me, or the range of D would be. Here's another example of mathematical process that you've probably seen before. And if you've had Calculus 2 or 3, then you've seen a lot of this. But it is sequences. We can regard sequences as mathematical functions. So what I mean by a sequence, just to refresh your memory, something like this, where I define like, a 0 to be 1. Actually, let me change that. Let's define a 0 to be 0. A 1 to be 1, a 2 to be 4, a 3 to be 9, ... So what I'm doing is I'm defining a n just to be n squared. So this is a really basic sequence, and I even have what's called a closed form of that sequence. I just square whatever n is. So how can this be thought of as a function? Well, the domain is going to be an infinite subset of the natural numbers union 0. Okay, the reason I have to union 0 in is because some sequences start at 0, like this one, some sequences start at 1, but the domain is going to be some infinite subset of the natural numbers union 0. So for this particular example, I have a function f that goes from the natural numbers union 0 to the real numbers. And the way this function works is f of n, anything in the domain, is just equal to n squared. So I can regard that sequence as a function. You can regard any sequence as a function. You may not always be able to find a nice little formula for it, but you can always regard a sequence as a function. And we also have what are called multivariable or multivariate functions. Now, if you're in Calc 3, you've had Calc 3, you've been dealing with these guys for a while. So here's a little video to illustrate this idea of what's going on here. Actually, before I do the video, let me just point this out. Like I mentioned earlier, this right here is called a Cartesian product or a cross product. And recall that the set A cross B is defined as ordered pairs AB such that A is in A and little b is in B. So if we define a function from, say, A cross B to C, let me name it F, then F is going to take as input an ordered pair. Now, technically, I need to have little extra parentheses in there, but we sometimes don't write those just because it looks better not to. So this is a little bit of what I talked about early in the semester, a little bit of abuse of notation. So we don't always put those extra parentheses in there. So I have f of AB is equal to some little c. Now, depending on what these things are, c could be the sum of those two. It could be some algebraic operations on those. It could be a lot of different things, but that's how that works. Now, here's a little video illustrating how this works that is very Calculus 3-ish. Okay, so we are going to look at an example of a multivariate function, a multivariable function. So unfortunately, this technology I'm using right now, I can't have nice, pretty LaTeX rendered code. And so instead of me trying to do it with my mouse, I use the keyboard. So I'm going to define a function from R cross R to R. Just going to be a nice simple one. F of x of y is going to be x squared plus y squared. So that's going to be the function that we're going to do. And if you've had Calc 3 or you're taking Calc 3 right now, this is going to be super familiar to you. But I want to stress the idea of how this is a function from R cross R into R. So my domain now is R times R, or R cross R. My codomain is R. So what would the range of this be? Think about what the range of this might be. It's going to be a subset of the real numbers. So I'm taking ordered pairs and I'm mapping them into real numbers. Okay, and I'm going to use GeoGebra 3D to kind of graph this. So I'm going to first of all, define a function, f of x and y, x squared plus y squared. Whoops. X squared plus y squared. So there's my function. Okay, right there. Let me kind of reset that angle and there. So it's like a cone. It's like well, think about, I don't want to get too much into Calc 3 stuff, but think about why this looks like this, Let's set this so that the green one is my x-axis, the red line is my y-axis. If you just graphed just the x squared part, okay, you would get a parabola. If you just graph the y squared part, you'd get a parabola. So it's like a parabola that has been rotated. Okay, it's like a parabola that's been rotated around to get the whole thing. Now, the point of this is to stress the function from r cross r into r. So I'm going to plot a point 1, 1, 0. So that is right there at A. Hopefully you can see that right there, okay? Now, what does that tell us? The 1, 1 is the input for my function. This is where the input is for my function. And now if I want to see what the output is, I would plot 1, 1, and then the output of my function, that is 1 squared plus 1 squared, well, that's 2. So that's going to be on my little cone shape right there. Can you see that extra, where that extra point is right there? That point right there. If I pull this up, you can see how they perfectly line up as I line this up right there. So this is a function, and its input is ordered pairs of real numbers. So the input is going to be things on this xy plane, and the output is going to be on this three-dimensional shape. But what I want you to realize is, the graph is going to be on this three-dimensional shape, but the output is going to be things along this z-axis, this up and down axis right here. So this point matches the point 2 on that line, and so that's how that works. So my inputs are real numbers, pairs of real numbers, and outputs are numbers along this axis right here. And then we have the graph of it, which ends up being this this really nice looking parabolic shape. So again, part of this is to illustrate the function thing. Another part is to show you GeoGebra 3D. Google GeoGebra 3D if you've never seen it before. It's a little bit more user-friendly than using Mathematica or something to graph it. Of course, it does less things, but it's still nice to get a little intuitive idea of what these graphs would look like. Let's just look at one more. Let me get rid of these points. I haven't tried this, so I don't know what this is going to look like, but let's do something like, I don't know, sine of x, let's say sine of xy plus x. I have no idea what this looks like. Look how cool that is. Okay, so let's see. That is so cool. So this takes as input x and y, and it outputs sine of x times y plus x. And we get this really cool shape right here. All right, well, that is all that I wanted you all to see as far as this goes, these multivariable functions. All right, now we're moving on to the section 6.3 material, where I'm going to define some adjectives to apply to functions and some other names we can give them if they satisfy certain criteria. The first of which is an injection, or an injective function is another way to say that. So start out with a function. So f is a function from a to b. A is our domain, b is our codomain. And then the function is called an injection, provided this definition is satisfied. For every x1 and x2 in the domain, if x1 is not equal to x2, then f of x1 is not equal to f of x2. Basically, it says if I take two different elements in the domain, they have to always map to different elements in the codomain. Okay, that's what injection means. A term that, this may be kind of familiar to you because this is usually what we call a one-to-one function. This should be familiar from calculus, from algebra, with the vertical line test. But it's more general than that. This works with functions that aren't necessarily from the real numbers to the real numbers. And this will play a big role when you get to abstract algebra. So anyway, like I was saying, if f is an injection, we say that it's 1-to-1, or we say that f is an injective function. So this definition has all these inequalities in it. So proving something is an injection isn't always straightforward to do because of these inequalities. So when you want to show something as an injection, you have two options. First one is you use the definition as stated. You show that for every x1 and x2 in A, if x1 is not equal to x2, then f of x1 is not equal to f of x2. We don't use this very often. Usually what we use is the contrapositive of this statement. That is, we show that if we start out with an x1 and x2 in the domain, if f of x1 is equal to f of x2, well, that implies x1 has to be equal to x2, okay? And these two statements are equivalent because they are contrapositives of one another. Now, to show that something is not an injection, that's when we typically use the first definition right here. To show something is not an injection, we find some specific x1 and x2 that are not equal to each other, but their images are. Their images are equal to each other in the codomain. So again, now this is not a hard and fast rule, but this is generally how it works. This is the one we use when we're showing something is an injection. So I'll say is an injection, and you can copy this down in your notes. And generally speaking, this is what we'll use when we say something is not an injection. This is the kind of the process we'll go through. And we'll see some specific examples of that right now. So before we look at kind of more mathy algebraic examples, let's just look at this simple one where I have the sets indicated with these bean diagrams with the elements represented as 1, 2, 3, and A, B, C, D in the two sets. I'm going to define a function f from A to B like this. 1 is going to get mapped to A, 2 is going to get sent to D, and 3 is going to get sent to C. So you can write out specifically what this function does if we wanted to. So f is a function from A to B. F of 1 is equal to A. F of 2 is equal to, what did I say? I said D. And f of 3 is equal to C. So this is a function because I've specified where every element in my domain goes. And so I have these three elements. Now, when you have small finite sets like this, it's easy to check that this is an injection. As long as I take two different elements over here, they always map to something different. Now, I want to contrast that with another function. I want to contrast that with this, and I'm going to use a different color for this one. So now, let's let C be the set. Actually, I'm going to use the same sets. So I will go ahead and call this A, 1, 2, 3, and I'll call this B, A, B, B, C, D, and a function. Now I'm going to call this function G, and I'm going to let 1 be sent to D. I'm going to send 2 to C, and I'm going to send 3 to D. So G is a function from A to B. G of 1 is equal to D. G of 2 is equal to C. And G of 3 is equal to D. Okay? Now, it's pretty easy to see that this side gives us an injection because whenever I take two different elements in the domain, they go to two different elements in the codomain. And when you have diagrams like this, it's easy to see because all of the arrows go to different elements. However, over here on the right, this G function, this is not an injection. Or you could write that as not injective. But I'll use the noun version, not an injection, because I have the element 1 and the element 3. These are two different elements in my domain getting sent to the same element in my codomain. And you can see that because both of these, 1 and 3, both kind of get shot to the same target element in B. Is kind of how you can think about it. Now, these first two examples, I'm not going to say too much about. This would be nice for you to look at it and figure it out for yourself. You could probably see just from looking at it, but it's a nice practice to draw the diagrams to get really familiar with how those arrow things work. Like I said, it'll be useful when you get into abstract algebra. So let's look at this third example here. So I'm going to define a function from z to z, from the integers to the integers, by f of m is equal to 3m plus 2. So how do I determine whether or not something like that is injective? So what we do is we take two elements in the domain. So I'm going to let m1 and m2 be in z, and I'm going to assume that their images are equal. That is, I'm going to assume that f of m1 is equal to f of m2. Now, remember, hopefully you wrote the definition down. If you didn't, scroll back on the printout version that you have, and remember that to show that a function is injective, we assume that we take two elements in the domain, assume that their images are equal, and now what we're going to do is we show m1 is equal to m2. And how do we do that? We just use the definition of the function. So we have f of m1 is equal to f of m2. This is what we've assumed. This is absolutely true. Well, that means that 3m1 plus 2 has to be 3m2 plus 2. Just using the definition of the function right there, just plug in m1 into here and m2 into here. And now you just do some algebra. I can subtract 2 from both sides and get that 3m1 is equal to 3m2. And then I can divide both sides by 3. So m1 is equal to m2. Well, we assumed that f of m1 is equal to f of m2, and we showed that m1 is equal to m2. Well, that means we've shown that, so that this algebra is true. So that means f from z to z is injective. And I'm using the adjective form on purpose because you need to be comfortable with both of them. Okay, that is an injective function. All right, next example. Now I'm going to have a function defined from R to R. H is a function from R to R, defined by h of x is equal to x squared minus 3x for all real numbers x. Let's see if this one is injective. So let's try to play the same game. If you've thought about this for a second, you'll realize what the graph of this looks like. The graph of x squared minus 3x looks like. It's a parabola, right? So that's a quadratic function, which means it's going to fail the horizontal line test for 1-to-1. So this isn't going to be injective, but how can we see that analytically? Well, let's let... And I say that, as I say that, I realize I may have said vertical line test before when I was talking about one-to-one functions. Obviously, I meant to say horizontal line test. The vertical line test is a test to see if something is a function. The horizontal line test is a test to see if it's one-to-one. So I apologize for that. All right, getting back to this problem, let's let x1 and x2, oops, not y2, I didn't mean to say that, x1 and x2 be real numbers, and assume that f of, not f, assume that h of x1 is equal to h of x2, then that means that x1 squared minus 3x is 3x1 is equal to x2 squared minus 3x2. Huh. Well, this is a little bit ugly. Not much we can do with this, right? There's no way we could get the x1s and the x2 alone on both sides of the function. And even if we did try to say, you know, what if I just said, look, I'm going to factor out on x1, that'll give me, you know, x1 minus 3 equals, well, that's not going to do anything. I have a mess anyway. So what if instead of trying that, we decided to, you know, let's get the x1 squared, this one over here, maybe we could do something with that. Minus 3x1. Maybe you'll take a square root of both sides, but then you have to deal with the plus or minus terms, you know, and that's going to change things around. Excuse me, that's going to mess things up. So no, that's not going to work either. So maybe this whole approach is wrong, and you suspect that maybe this isn't going to be an injective function. And then you think about, oh, wait, I know some calculus. I know some college algebra. So I know that this is going to fail the horizontal line test. So maybe instead of trying to show that this is injective, maybe we'll just illustrate why it's not injective. Let me get all this erased. So let's see if we can go through the process of showing this is not injective. So recall how that worked. We want x1 and x2 that are not equal to each other with their images equal to each other. So we got to find some specific elements that are not equal but do have equal images. So why don't we try to factor this? And that'll give us an idea of what the function might look like. Or rather factor it so that we can see where the zeros are. Well, that means that x times x minus 3 equals 0. So x is equal to 0 or x is equal to 3. Well, we're done. This is it. We found two different numbers, 0 and 3. But if we plug them into here, you know, they're both going to go to 0. So x equals, so if x1 is equal to 0, x2 is equal to 3, clearly x1 is not equal to x2, but h of 0, or rather let's write this as h of x1 is equal to 0, and h of x2 is equal to 0. Well, we found two numbers that are not equal, but their images are equal. So that tells us that h, a function from R to R, is not an injection. Okay, the next extra bit of terminology we can add to functions is surjection. So start out with a function from A to B. The function is called a surjection, provided that the range of f equals the codomain of f. Okay, what that means is, this is a more formal way to use the definition. Excuse me, this is a more useful way to write the definition. For every y in B, there exists an A such that f of x is equal to y. Okay, the range is the whole thing. The range is the whole thing. So look how this definition is stated. We start out with an arbitrary element in the codomain, and we show there has to be something in the domain that gets mapped to it. So when f is a surjection, we also say that it is onto. It is an onto function, or that f maps A onto B. And in the adjective form, we say that f is a surjective function. To show that f is a surjection, we have to show that for any y in B, we can find an x in A such that f of x is equal to y. To show that f is not a surjection, we got to find a specific y in B such that for every x in A, f of x is not equal to y. So we're going to do some examples of how this works. All right, so let's start out with this one, with some finite sets. I'm going to do the first one. I'm not going to do the second one. I'll leave that one for you all. So here we have a function k from A to B defined as given. K of A is equal to 4. There's this arrow. K of B is equal to 1. K of C is equal to 3. So there we go. So is this surjective? Well, no, it doesn't. It isn't, because I have 2. 2 right there. Nobody gets mapped to 2. Nobody gets mapped to 2. So there is no x in A so that k of x is equal to 2. So k is not a surjection, because I have somebody in my codomain that doesn't get hit by an element from my domain. Said another way, the range of A is not, the range of K is not the codomain of K, because I have this little extra element right there that doesn't get hit. So this is not a surjection. Next example is an algebraic one. Define f from R to R as f of x is 3x plus 2. All right. Now, you may think about the graph of this function. It's a line. And think about how you found out whether when you were determining what the ranges was of graphed functions. Okay, and the range of this f is all real numbers, which tells you that it is going to be surjective. So how do we show that? How would we show or how would we prove the claim? I don't want to use red. How would we prove the claim f from R to R where f of x is 3x plus 2 is, I'm going to use the term onto, because you need to learn to be flexible with these things. Okay, so let's prove this. So what we need to do, we need to let y be any element of R, just an arbitrary element. We need an x in R so that f of x is equal to y. That's what we have to do to prove that this is a surjective function. Now, there's a little side work involved. So here's my side work. Okay? 3x plus 2 has to be equal to y. We can figure out what x has to look like. That means 3x is going to be y minus 2, and x is going to be y minus 2 over 3. Okay, this is the side work for your proof. Now let's go back to the main part of the proof. And we're going to let x be equal to y minus 2 over 3. So it's important to note that this is a real number. Okay, that's what has to be true. X has to actually be in the domain. So this is a real number because y is a real number, 2 is a real number, 3 is a real number. So closure. By closure of subtraction and division, the real numbers, non-zero division, this is a real number. Okay? Then f of x is equal to, well, I'm going to sub in to what my function is. This is going to be 3 multiplied by y minus 2 over 3 plus 2. This is going to be, the 3's cancel, y minus 2 plus 2 equals y. And that's the end of the proof. We did it. We found an x such that f of x is equal to y. And so this is a surjective function. Okay, next example. Example 3, or problem 3, looks a lot like problem 2, but notice I have different sets involved, and that's going to change things pretty dramatically. So what would happen if we tried to play the same type of game? Okay, what would happen if, I took, say, an n and z, and I wanted to say, well, let's solve 3m plus 2 equals n. Well, that means that 3m is going to be n minus 2, and m is going to be n minus 2 over 3. Well, there's the problem, because now we're dealing with integers, okay, with integers, and depending on the value of n, this would no longer be an integer. On the previous example, I stressed that x, we defined it as y minus 2 over 3, that was a real number. But now, this may not be an integer. And in order for it to be a surjective function, this would have to be an integer for every possible n that I could pick. So this one is not surjective. So how would we do that? So my claim now is that f is not onto. Okay? And so the proof of this, we could just let 1 be in z, and there is no m in z such that f of m, which is 3m plus 2, is equal to 1. There is no integer solution to this, because if there was, it would look like this. 3m equals negative 1, m would be negative 1 over 3, but this is not an integer. And so that's the end of the proof, because I can never find an m in z that would hit 1 as a target. So this is not an onto function. Okay, last one. If we have a function that is both an injection and a surjection, we say that this is a bijection. A function is a bijection if it is an injection and a surjection. It's a function that is one-to-one and onto. We describe it as a bijective function. To show that a function is not a bijection, we either have to show that it's not an injection or that it's not a surjection, or both. Okay, so let's look at some functions and figure out whether or not they are bijections. And we're going to justify everything. Now, this is an exercise that you're assigned for your homework, so I'm not going to work all these out. I'm just going to give you some advice on how you would approach these. So the first one, a function capital F from R to R, defined as 5x plus 3. Now, first of all, think about what the graph of this looks like. This is just a line with slope 5, y-intercept 3. It's going to pass the horizontal line test, so you know it's injective, and its range is all real numbers, so you know it's surjective. So, yes, this one is a bijection, and you have to show that. And the examples that I did, you'll just copy those examples to show this is one-to-one. You'll just take an x1 and an x2 and do some algebra to show this is an injection. To show that it's a surjection or that it's onto. You'll do it just like the previous example. Next one, capital G from Z to Z, defined by this. Okay, now this one is not, or let's not say not, let's say no. This one is no, this is not a bijection, okay? So where does it fail? So here's the hint. This is injective, it's not surjective. So figure out why. It's like the example we did a few minutes ago. All right, this one is fun. Not hard, but I like the way that it's defined because this is a unusual looking domain, okay? So now I have a function from R minus the number 4. And I have to do that because look how the function is defined. It's 3x divided by x minus 4. This function isn't defined when x is 4, so I have a restricted domain here. So a function from r minus 4 to r, defined this way. Okay, is this a bijection? To get an idea, maybe graph it. One of your favorite graphing programs on GeoGebra that you saw on the multivariable video a few minutes ago, or on your calculator, whatever. You know, look at the graph of it. Does it pass the horizontal line test? Does it look like the range is everything? That gives you an indication, but you're going to go about doing this the same way as we did the other ones. And now I have not only a restricted domain, but a restricted codomain. Okay? So think about your answer in part C, and then how are things going to change when your domain is R minus 3? Okay, what changes when I don't consider 3 as part of my codomain? And finally, here's one another problem for you to solve. That is not this function isn't like algebraically given. I have a function from the natural numbers to the natural numbers, where d of n is the number of natural number divisors of the element n. Is this an injection? Is it a surjection? Justify your conclusions. So I want you to kind of work through this one, but let me show you an example of what this is talking about. Okay, what would d of 1 be equal to? Well, what are the natural number divisors of 1? Well, the divisors of 1, the natural number divisors of 1, there's just one. It's just the number 1. So that means that d of 1 is just equal to 1. So I'm going to do it in a different order over here. The divisors of, well, let's see. The divisors of, say, 12. This is the set. Remember, only natural number divisors. What do I have? I have 1, 2, 3 goes into it, 4 goes into it, 6 goes into it, 12 goes into it. So those are the natural number divisors of 12. So that means that d of 12 is 1, 2, 3, 4, 5, 6. This is 6. Okay. One more example that'll kind of help you do this problem. What about d of 7? 7 is a prime number. So the only divisors it has are 1 and 2, or excuse me, 1 and 7. In other words, only 2 divisors because it's prime. So think about that. Figure out if it's an injection, if it's a rejection, and then justify all of your answers. And this is it, guys. This is the end. I may do a few more videos if people have a lot of questions about things. Hopefully, I'll see you in the office hours over the next week, or schedule extra time. But that's it. This has been a really, really fun class. The first, 2/3 was a lot more fun than the last third. You were a good group, and it's really unfortunate the way things turned out. But I think you're all going to be okay. You're all hard workers. Stay in touch. If you have trouble with things in your future classes, let me know. I'm always available to help you. And if I don't talk to you again, have a good summer, and hope you and your family stay safe. I'll talk to you all later, hopefully. Bye-bye.